All right, good afternoon. Let's start lecture. So I started the review, so let's finish it. Probably not going to finish everything today, but let's try to finish most of them. Basically, what we have started is on the review of loading and the type of stress corresponding to different type of loading. But if you have if you have a typical system and you always start with a stress element, so basically how you can extract a stress element out of the existing system and then draw this stress element, the loading condition properly, okay, and that's your starting point. So knowing what type of stress exists for that stress element is important, so because that's the fundamental part that you can analyze your system. And I started by categorizing what type of stress that we have seen and what type of loading condition will cause that type of stress. So it's very simple. You know, there are only two main types of stress: normal stress and shear stress. But the loading condition or the cause for the stress, you know, could be different reasons. So, for example, normal stress can be caused by pure axial loading, okay, compressive or tensile, or it could be caused by the so-called bending moment. So when you bend a bar, when you cut a cross section, and there will be bending normal stress, right, due to the bending moment. Shear stress, it can be caused by direct shear. So if you have a scissor cutting something, or if you have two plates bolted by a rivet, a bolt, so and that cross section of the bolts, okay, could be undergoing this direct shear. And the same thing if you have a bar that is undergoing actually a bending moment or with some loading conditions, okay, distributed along the bar, then there will be also bending shear at the cross section of the bar. And lastly, which is the most common, if you twist or torque a certain an object, then the cross section will experience the torsional shear. So those are basically the fundamental stresses and the cause for that, right? So let's going from each one of them, okay, starting from this normal stress. And let's look at the normal stress due to axial loading. Okay. So it's a very simple case. If you have a bar, whether it's a circular bar, right, or not, doesn't matter. Let's say we have a circular bar right here, subjected to a tensile force F on both ends. Now we're going to cut a cross section. Okay, we're going to try to cut a cross section anywhere along the bar right here. And if we look at the cross section, suppose that this is a circular bar, for example. Okay, and we typically, let's say this is a y-axis, and this is your x-axis, and this is your z-axis. Okay, so this is your almost like the right view, okay, of this circular bar. Okay. Then your normal stress in this case is basically the force over the area, okay, cross-section area. Okay, so cross-section. This is your cross-section, and in this case, what it means is basically doesn't matter where the cross-section is, maybe here or here, doesn't really matter. So it's all the same value basically. So if you look at the normal stress, okay, on that cross-section, it's all sigma equal to F over A. Okay. So that's the first type of simple normal stress due to axial loading. Okay. All right. So the next one here, let's look at the normal stress due to this so-called bending. Okay, so bending here. If you have a bar, if you try to bend it, okay, then each cross section, any cross section, will experience this bending normal shear, the bending normal stress. Okay, so I'll use a circular bar for the same purpose of illustration. So let's say we have a circular bar over here. Now we're going to bend, let's say, apply a bending moment, okay, in this direction right here. Okay, so you bend it like that, right? Yeah. We'll establish, let's say, the coordinate systems similarly like the previous case. So x, y, z. Okay, x, y, z. So now the way I draw it here, okay, a couple of very simple concept here. So the z-axis, okay, so the z-axis here to here is called the neutral axis. Okay. And that's basically, if you curve your hand for the moment m, that's basically where your thumb is pointing to, right? The moment. Okay, so the moment is about the z-axis. And of course, if your moment is the other way around, then the moment is pointing the other direction, right? Yeah. Okay. So z is called neutral axis right here. Okay. Now, for the first week, especially in the tutorial, you will review how to draw bending moment diagram, shear force diagram, and torque diagram. According to my experience, I think that at this stage, there could be a bit of confusion in terms of the so-called positive or negative conventions. Okay, so there are different conventions, and I actually will talk about maybe a couple of conventions in today's lecture when we come to the Mohs circle. It really boils down to the situation in terms of which one is positive, which one is negative. That's what the conventions basically means at here. Okay? Say, for example, a very simple convention. If I draw a bending moment like this, so what do we consider the bending moment as a positive, or when do we consider as a negative? If I have a bending moment draw like this, what's the convention for positive?
It's positive because it's bending upwards like smiling.
This one is actually is bending upward or downwards? This one is bending this way, right? It's smiling, yes, right?
Smiling is positive, and then frowning is negative.
Good, yeah. That actually is one positivity. But let's say when you in your statics, right? When you know first your statics, and you want to know what is positive moment and the negative moment, and how do you define that? Clockwise or counterclockwise. So counterclockwise is considered as positive, right? So that's one positivity or negativity, right? Yeah. Now, what your positivity actually considered negativity is actually when it comes to the drawing of the bending moment diagram. When you this way here, it's considered a positive bending moment, and when it's keeping this way, it's considered negative bending moment. Yeah. So that's the first week. I want you to be aware of this. There's different positivity and the negative convention basically at here. Okay. Yeah. And just like a force, let's say if I have a force, pointing to the positive axis direction, is considered, let's say, positive, right? Yeah. However, when you come to the drawing a shear force diagram, it's not that just like that. It's actually relative to the cross section the shear force is applied to. Okay. If it's causing the cross section going clockwise or counterclockwise, then there's this negative, positive things. Okay. Yeah. So just be aware of this thing here. Okay. So let's come back to this bending normal stress due to the bending moment. If I look at the cross section, basically if I cut a cross section anywhere, okay, if I cut a cross section anywhere along this bar at here, and suppose, let's say, I'll look at in the front view at here. Okay, so let's say this is a front view of the bar at here. So this is the cross section we cut over here. Then what will be the distribution of the normal stress due to this bending moment? If you recall that, what's the distribution bending moment? It distributes the bending moment cross section like this. For this particular case, okay, for this particular case, and this forms a linear lines at here, okay, forms linear lines, and that's your bending moment applied to these directions, right? So you will have a distribution of a normal stress along the cross section, which is a circular cross section, actually, right? you have that. And the formula for that is a sigma. So let's say in this case here, right? We're talking about this is your x-axis, okay? So this is basically the normal stress in the x-axis direction. And let's say I'm interested in what will be the normal stress at this location, right? So at this particular location, which is a location that is basically y distance from this origin here. So let's say this is your location, right? So this is your y distance to that location. Then the normal stress at that location is negative m times y, and then divided by I at here. Okay, divided by I. That ring a bell, right? So more formal writing at here. Okay, this is m, and this m is basically we turn in terms of the z-axis. So we can write a subscript z, and the I is can also write as iz. So if you recall that this iz at here, okay, it's called the second moment, okay, of area, okay, about the z-axis. Okay, second moment area. So when you cut a cross section, right, it's about how hard is it to rotate that area about the z-axis. That's basically called moment of area. It's not a moment, it's a moment inertia concept, but it's not a moment inertia for a 3D body, right? It's the moment inertia for a cross-section area, okay? And it's a second moment in area. So apparently there is also first moment area. So that's actually the polar moment area. So that's the next one. So this is your second moment of area at here, right? So this iz, okay? Yeah. A quick question. I have a negative sign written at here. Any reason for why there's a negative sign at here? Because it is compression, right? Yeah. So this is a very, very accurate writing of this kind of normal stress. But in our case, future, okay, in the future, most of the time, actually what you care is about the maximum or the minimum or just the absolute value, okay? That's actually what really matters. So you don't have to stick to the most accurate way of writing, okay? So for example, in this case set here, right? I'll point out a few minimum and maximum here. For this one here, which location has the minimum and maximum? So apparently the location on the two edges, okay, at the top and the bottom, will have the maximum value, absolute maximum value, right? So this one here, you have a maximum value, which is compressive, and this one here you have a maximum value, which is the tension, right? Yeah, tensile stress. So maximum. So this is basically, in this case, your normal stress due to the bending. Maximum at top or bottom of the cross section. Okay, so that's what you have to always remember. For this is the normal stress due to the bending. Your maximum location at either the top or the bottom. And in terms of this second moment area I added here, in this case we typically just only worry about two very typical cross section. One is a rectangular cross section, and the other is a circular cross section. So for rectangular cross section, say this is your, let's say if this is a cross section, you cut like that, okay, and with a B at the bottom and an H, okay, over the other sides, okay. Your IZ, okay, is basically 1/12 and BH cube, okay, BH cube. And there's that trick. There's actually a trick to memorizing this formula. So the B at here is a quantity parallel to the neutral axis, which is the rotational axis. Okay, yeah, and H is the one perpendicular. So for rectangle one, let's say you happen to want, what you want is IY. And guess what's going to be the formula now? 1/12. That's right. Sorry, HBQ, right? Yeah. So that's your rectangular cross section. But of course, in most of our case here, this is our convention here. This is your Z, and your moment is applied about the Z-axis. So that's your formula for this. Okay. Yeah. If you have a cross section which is a circular cross section, so for a circular cross section, okay, the IZ, okay, is actually doesn't matter now. Same as IY. It's basically the same as any axis that goes through this origin there. Okay, so the results is pi if the diameter of this circular cross section is d, okay, then IZ or IY is pi d to the power 4 over 64. Okay. Now remember, this d here is the diameter. Okay, yeah, because I have seen in the past some common mistakes mix the d with the radius, right? Yeah, so the completely different results, right? Yeah, and you can always replace the d with radius, and you will see if you place the d with the radius, let's say d is 2r. So this one, what would that be? So it's a pi times 2 to the power 16, r to the power 4, and then 64. So it's pi r4 over 4, right? So it's different, okay? Yeah. If you're interested in how this is derived, I can show you off the lecture. That's okay. Yeah. But the formula-wise for calculating normal stress due to the bending, it's m times the max from the origin to this distance over here, okay, and then over the I, and you'll get the maximum there. Okay. Okay. So that's normal stress due to bending. Before we move on to the shear stress, and here's a very common case, okay, for a bar to be loaded, which is the so-called the two-plane bending condition. Okay. Okay. So two-plane bending. I'll focus on the circular bar, which is a shaft. Okay. Yeah. So let me illustrate this situation here. What do we mean by two-plane bending? So let's say if you have a bar, okay, attached to a wall or something. So let's say we have a bar attached, okay, to the wall at the one end, for example. Okay, yeah. And the bar has a diameter of d. So x-axis is this way at here. Okay. And now here comes the loading condition. So then what happens is you're going to load this bar, you're going to bend this bar actually. One way is to bend it, okay, this way. Okay, so that's one way of bending. So let's call this is one moment at here. Okay, yeah. So it's basically it's like you're bending horizontally like that. Okay, yeah. And then the other direction of bending could be, okay, this way here. So you're bending it in the XY plane like that, right? The first one is in the XZ plane, and the other one in the XY plane. So that's called the two-plane bending. Okay, two-plane bending. Two-plane bending is very common, especially when you are dealing with a shaft. Okay, so when you have a shaft, you may have a loading in this direction, which is this is your, let's say this is your XY plane, and the same thing in the XZ plane, and you might have another type of loading condition. Okay, This is your z now, okay, in the xz plane. So this loading condition will result in bending moment, okay, in each plane. Okay, that's basically where the two-plane bending will from. Okay, so let's say if I'm gonna denote the symbols that are here. Let's say if I'm gonna denote I'll use this as origin and here. So for this bending moment, okay, I'm gonna draw a vector right here. So I'm gonna call this as my. Okay, right. This is a vector. It's my. So that's how you indicate a moment, right? Yeah. And for this bending moment, I'll indicate this one as mz. Okay. So that's the two bending moment, right? Two bending moments. Okay. So now comes the question: how do we calculate, let's say, the maximum normal bending normal stress due to this two-plane bending at here? Okay. So the idea is basically what will be the maximum bending normal stress? Okay, that's the idea, right? Okay, so to calculate this bending normal stress maximum, we use basically a linear algebra or vector addition here to solve this question. Because you have a moment this way, you have a moment this way, and these two moments are literally just perpendicular to each other, right? Yeah. So we can basically find the resulted, okay, vector addition, okay, by adding these two vectors together. So let's say we call that m at here. Okay, we call the m. Like it? Okay. Okay. So before I move on here, when I draw the M like this, right? When you draw the M like this, how can you visualize how this circular bar is being bended with the notation of M moment? Right? Can you visualize this? Okay. So you have the direction of M given at it here, and you also has the literally the same magnitude, for example, right? Yeah. How is the bar being bended under this M at here? So use your hand. You know, M basically represents what? The direction when you curve the bending. When you curve up the bending, the thumb pointing to this M here, right? Yeah. So if I visualize this bending or trying to draw, let's say, a circle like this representing this bending, I should try to draw what? It's not very accurate, but you should try to draw a circle, right? Or, you know, with a curve that is perpendicular to this M at here. Does that make sense? Right? Yeah. And now also ask this question at here. If this is a cross section, right? If this is a cross section in here, so here's a cross section, and here is your bending moment. Okay, yeah. So where would be this maximum location on the edge of this circle? Yes.
Along the M vector, at the very edge of the circle.
You mean here and here?
Yeah.
Not quite. So this is why I want you to visualize how it's being bended, right? So it's being bended. The bending plane is actually perpendicular to the M. Okay. The notation you gotta be careful. The notation of M doesn't mean you're bending this in the M direction. That's right. That's right. So your minimum and the maximum location is actually where you draw a perpendicular. So this is not a minimum maximum, but your maximum location is going to be either this location or this location right here. Okay? Yeah. And now you can think which location has tension, which location has compression. So the A will experience what? Compression, right? Yeah. And the B is tension. Okay? Yeah. Very good. So this is the sort of things that down to the details when you analyze this. But it's not necessary in the long run, not necessary for all the questions here. But at this stage, I would encourage you to try to understand really what's going on at here. Okay? Yeah. Okay. So let's calculate the addition of the M, and then we can find a formula for the maximum value of the bending normal stress. Okay. I'm going to use, let's say, this symbol representing its magnitude. Okay, so basically, get rid of the vector signs. Its magnitude is mz. This is my, and this is your m here. Okay. Yeah. So your vector addition, because this is perpendicular. Okay, this is perpendicular here. So your m is basically my square plus mz square. Then your maximum bending normal stress, which is at either A or B location, okay, it's m times the maximum location distance, which is half of the diameter, and then divided by the cross-section's second moment of area. So we plug in the formula here. M is this guy, so I can my square plus mz square 1/2 square root, and then times d over 2, and I is pi d4 over 64. So overall, you get a 32 times pi d to the power of 3. Okay, pi d cubed. That's your maximum. This is your two-plane, basically two-plane bending scenario. Okay, you get to know basically where it is and what the values of maximum is. Okay. Okay. Any questions so far? Okay. Okay, so I think we're done with the bending normal stress now. Okay, so let's look at shear stress. The first type of shear stress, as I listed, is called direct shear. Okay, direct shear. So direct shear is a type of shear stress. You know, when you have, let's say, when you have three pieces of bar bolted together, okay, and if you have a force over here, half a force over here, okay, then at the cross section, okay, on the bolt, you will see the so-called direct shear, because this is a direct shear loading, okay, direct shear loading, like a scissor cutting, that type of things, right? Yeah. So in this particular case, if you look at the cross section of the bolt, then you see the direct shear, and that value of the shear is basically the force over the area, right? And the force is 1/2 of F and divided by A, so you get this F over 2A. That's your direct shear. Okay, that's direct shear. And another scenario for direct shear that you often see is, let's say, if you have a cross section like this, okay, and it's fixed on the wall, and then it's being a force is applied to this cross section, okay, and this cross section is A, and then you consider it's a direct shear on the cross section, so the shear stress is F over A. Okay, yeah. So the difference here is actually you'll see the difference right away when we look at the other type of shear stress due to the bending. Now for this cross section, this is a very small cross section. Okay, small cross section. Small cross section, you can consider the shear stress across that section. Cross section is very small, so everywhere, any locations on the cross section has the same value of the direct shear, this value here. And same thing for this one here, and you are also assuming, okay, whether it's this location or that location, so any locations will have the same basically shear stress, right? Yeah. And that's the calculation of the direct shear. However, this is actually particular for this case. If you have a area relatively big enough, the shear stress distribution is not an even distribution across everywhere, okay, along this cross-section area. So we need a new formula. So that actually brings us to the next one here. Okay, you'll see the formula. So let's see. This guy here is basically still shear stress, but it's due to bending. Okay, due to the bending scenario. Okay. So let me before I present the formula, let me explain a little bit. So what do we mean by shear stress due to bending, right? Okay. This is also will be explained in this week's tutorial. This is very common if I have a loading for a bar, that type of scenario. Okay, yeah. Let's say here is an example I really like to give to you. You have watched the sports of weightlifting, right? So when you see the athlete trying to lift a weight, okay, so then what happens is, okay, that's the basic structure of weightlifting. So you need to grab the bar, right, symmetrically, okay, along the bar, okay, and then you lift. You know, if you grab it, it's asymmetric. I don't think that's going to be good, right? So you need to grab it symmetrically. So which means maybe this side is L here, and this side in the middle maybe is a 2L, who knows, right? Yeah, for example, okay? Yeah. So the weight probably, you know, has a W, and then the force applied, okay, by the athlete, you can call it F, okay? So assuming the left and the right arms equivalent force. If you do a free body diagram, this is your free body diagram basically. And if you do a static analysis, and you'll be able to find this is basically your W and this is basically your W, right? Okay. So now, if I single out this bar area here, okay, so the bar is under a loading condition like that, right? Loading condition like that, okay? Yeah. So the question now is, if I cut a cross section, okay, anywhere along this bar, anywhere, okay, yeah, and we look at the cross section, okay, we look at the cross section, what will be the force or moment distribution basically exist at that cross section here, 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 right? So that's the point, you know. This is basically, if you can figure out all the possible location, you draw a curve, draw a graph, and what do we call that? That's basically called what? Exactly, right? Yeah. So for this one here, this is actually a very special case. Okay, if we start to draw the bending moment diagram and the shear force diagram, okay, so we use a V representing the shear force. So basically, if I look at this cross section, there might be a V at this cross section, there might be a bending moment this cross section, right, at that location. That's basically the idea. Then this week tutorial will do the review for you. Okay, you will see that for this loading condition, okay, you have basically a negative shear force. Okay, this is basically a kind of negative. Why the negative? If you can go to the tutorial, see that negative shear force from here to here, and then 0 from here to here, and up to this location you get a positive. Okay, like this. So that's the shear force distribution along this cross section. Okay, and we can draw similarly. We can draw a bending moment distribution, okay, along this bar due to this bending. And the bending moment distribution, if you draw that, it'll be looking more or less like this. Okay, and your bending moment distribution. Okay. And it's the negative. If you look at the bending moment here is negative, and then later you'll see the bar actually will curve up like that, right? Yeah. Okay. So now this is a very important information, right? Very important information, because what this information actually, there are a couple of things I can tell you. So if you look at this one here, let's say if I call this is A location, this is B location. If I look at the shear force distribution, what's the value between A and B? 0, right? And is the bending moment 0? And it's constant, isn't it, right? So if you recall that for the location between A and B, it's a very special case. It's called what? It's called a pure bending, right? It's called pure bending. Okay, it's called pure bending scenario. So this one here is called pure bending. Now, second of all, okay, let's say if I cut a cross section between this side and A location here. Okay, if I cut a cross section somewhere around here, okay, and then let's see my cross section, right? This is your cross section for that location. So at this cross section, you would have, let's say I have a shear force applied to this cross section. Okay? Does that make sense? So now the question is, because of this shear force V, so this V here is shear force, because the shear force V, what is the shear stress distribution along this cross section due to the V here? Now this is basically the idea, the shear stress due to this bending type of loading here. Okay? Yeah. So that's what we wanted to find. What does this tau equal to, right, along this cross section? Now you might answer, well, maybe tau equal to V over the area, right? But it's not. Because if you just use V over area, it's like a direct shear now, right? But the thing is that here is the shear stress at a different location, okay, will actually have a different values, okay, will have different values. Now, in short, to calculate this tau, okay, the formula for calculating the tau, I'll redraw it here, something like this, okay? Yeah, this is your cross section in here. Your tau calculation, the formula is VQ over IT. Okay, it's called VQ over IT. Did you guys learn in the mechanics material for this formula? Just ring the bell. That's okay. So V here, of course, is the shear force, right? The shear force. The Q and the T, the I at here, as usual, is that second moment, the area, just like the bending moment caused the normal stress caused the bending moment. Okay. The Q at here, basically, let's say if you're interested, is the shear stress at this location. Okay, so this is your neutral axis at here, right? Or z-axis. If you're interested in the shear stress at this location, then here's how you would calculate. This is your so if this is the area, this is your neutral axis, and this is your T here. This is your, if this is the location, right? So this location here, okay? At this location, the shear stress. So the T is the thickness at that location, and then the Q at here, okay? The Q at here is calculated. So suppose this is your, let's say A prime. This whole area, this whole region is A prime, and you can calculate the Q, okay, using, it's a double integrals actually, okay, y dA prime over this area A prime. So this Q at here is called first moment, okay, first moment with respect to the neutral axis, first moment of area. So this one here is the first moment of area, okay, with respect to neutral axis. Good. So that this formula is technically for calculating all of these shear stresses at the different locations. But you will have a shear stress, the same shear stress along this line here, the same stress along this line like that. Okay? Yeah. Yeah. So you plug in and you will do the calculation here. Okay? Yeah. So now if you think about it, right? You think about this, the calculation, just look at the Q value here, the Q here. So where do you think you will have the maximum Q value in this for any cross section? If you look at the cross section, the way to calculate the Q. The Q depends on what? Depends on this region, integration region here, right? So if you want to have a maximum Q which is on the top, which basically will result in the maximum tau, isn't it, right? Yeah. The maximum location must happen at which location for the shear stress? Which location will have the maximum shear stress? Location basically means this is your cross section, right? Is it going to be the top and the bottom location? Or is it going to be somewhere in the middle? Or is it going to be here? Top bottom? But at top the bottom, what at the top and bottom, what's the A here? A is literally what? Is 0, right? So the Q will be 0. So top bottom, I don't think so. Huh? Yeah. Yeah, T is also the thickness. But here there's a limit idea here involved here, right? So in more straightforward, let's just look at the Q value. Yeah, the Q value is basically determines where the minimum and maximum is. Yeah. So basically, wherever the Q is maximum, you'll have the maximum shear stress. Okay. Yeah. So in this case, when you have a circular cross section, the integration of the Q depends on this A. When you have a bigger A prime area, then you get bigger Q. So where would be the maximum location? Here, right? So basically, if I redraw this one here, if this is your cross section, then the shear stress distribution, it's 0. Actually, it's a 0 on the top, bottom, and then it start to increase. Okay, start to increase, and which will have the maximum at the neutral axis. That make sense? Okay. Yes. The thickness going across along the neutral axis. Yeah. Okay. So that's the idea of the shear stress distribution. Okay. Yeah. Now, when it comes to this course, I don't think you're going to be asked to calculate the shear stress for a very irregular cross section. And for this course, it's out of the purpose of design. And then often in time, we're only interested in the maximum location, and we're only interested in the maximum value, right? So what we're really interested in here is, for a typical cross-section, what is the maximum shear stress and where it is? And then now you know where it is. So let's say if we have a rectangular cross-section. Okay, rectangular cross-section basically means you have a cross-section like this. Okay. And here's your z-axis, the neutral axis. Okay, and here. Let's see close. And then you have basically a shear force V applied at this cross section, and now you got to know now the maximum shear stress is at the neutral axis location. Okay, yeah. Your tau at here, your tau max on this cross section for rectangular is 3V over 2A. Okay, it's 3V over 2A. Is that good? Yeah. And also, just on the same note here. Okay. So for stress analysis, right? For stress analysis, often what you do is you need to take a stress element. Now, taking stress element is you need to take a look at into the 3D sense at here. For example, let's say if I'm interested in a location at here. So then what you do is you can imagine you can cut a cross section, right? You can cut it cross section horizontally into this piece of wood or something. Okay. And then once you separate this thing here, so at this location you know that you have a shear stress tau at this location, which is calculated according to this. Okay. And if for the same location, right, everything is in equilibrium, then you must have a shear stress. You must have a shear stress pointing to the opposite direction at the same location. So this is tau. This is also tau at here. Okay. Yeah. So if let's say if I'm going to take a stress element. Okay. If I'm going to take a stress element out of this location, right? Let's say take a stress element out of here. So here is the proper weight. So you basically, this is your one side, and this is the another side here. One side here you just have a tau. Another side is have a similar. You have a tau here. Okay. If this is only loading, and there's nothing else, right? So that will be the stress element, like this. Okay. Yeah. So if you look at this simple drawing at here, right, it actually tells you a phenomenon. If you go to your basement and you watch the supporting beam, okay, for the basement and the wood, you know, often in time, what do you see? You probably see a crack, right, along the wood. In which direction? In the horizontal direction, right? Yeah. And where the crack is, how the crack is caused, is basically because of the shear stress at here. Okay. Yeah. And wood is an anisostropic type of material, so and you see a horizontal type of crack along the wood beam. So that's your rectangular type of a cross section. Okay. If we have a circular cross section, so circular one here, and same thing, maximum happens at the neutral axis location, and then the tau max at here is 4V over 3A. This is different, so it's 4V over 3A. In terms of the formula, this is what you need to basically remember, huh? Yeah. So now if you think about the two different stress, the normal stress caused by the bending and the shear stress caused by the bending, so the bending normal and the bending shear, the maximum happens at the different locations, right? Yeah, the bending normal happens at the top and the bottom, but the bending shear stress happens along the neutral axis. So that's a distinct difference between these two here. Okay. Okay, so finally, the last type, the torsional type of shear. Okay. So shear stress due to torsion. And this one is relatively easy to understand. Say you have a bar, and then you subject the bar, okay, apply a torque, okay, along this cross section of the bar. And then you're interested in the shear stress caused by this torque T at any locations along this cross section. How do we calculate? So here's your formula. So tau equal to T times rho over J. So rho is the distance from here to any location. So that will be the rho. Okay, so distance, the radial distance basically. T is the torque, and J is the so-called polar second moment of area. Okay. Polar. So polar is basically calculate the moment in area about the origin, okay, or about an axis going through the origin. So for circular one, okay, for circular cross section, your J is equal to pi d to the power 4 and over 32. Okay. And in this class, okay, circular is enough. So we typically will only consider a shaft which is circular. Okay. Yeah. So if I look at this formula for the shear stress, again, we're interested in basically in the location that give us the maximum value, right? Maximum shear stress, because that's the location you want to analyze and we want to prevent from the failure from happening. So it's pretty obvious when rho is equal to the radius, right, or the edge, along the edge, that's where you see the maximum shear stress. So bottom line is, the other thing I think you also need to be familiar is how you draw the shear stress. For example, if this T goes this way, at this location, you should draw the shear stress tau to be perpendicular, okay, to the rho edit here. So that's your direction in the tau. So same thing, let's say if I am interested in the location tau at this location, so then you should draw a tau perpendicular to that radius, and this tau here, so you have a maximum, so the tau will be T times R over J, right? T times radius over J. Okay. So that's it. That's all the different type of stresses and the cause of the stresses. Okay. And the next step, actually, we'll look at how we put things together, especially for failure analysis. If we have a given loading condition, how we can put things together, how we can analyze the failure or preventing the failure from happening, right? Okay. Yeah. Okay. Any questions? Okay. So let's continue in here. So now let's start putting things together. Basically, now we're going to answer a question is looking at this so-called the general state of stress. Okay, the general state of stress. Okay. So I'll ask you a question first. Okay? Yeah. If you recall what we just described the scenario for the bending, is called the pure bending, right? So let's say you have a beam, and that is under pure bending. Okay. So the question here is, so if you look at the pure bending, this is the scenario I was just saying here. So this location between A and B, you have pure bending. And pure bending basically means if you cut a cross section, okay, vertically, there's no what? There's no shear force, right? Okay. So, but then the question here is, if there's no shear force, the question here is there really no shear stress, or is there still any shear stress in the material? Okay. So that's a question. I want you to think about it for. And the same thing. Let's say this is one case, right? Let's say how about another scenario for a beam or bar in uniaxial tension, for example. And how about this loading condition? So if you have a, let's say, a shaft, you just load it axially, right? If you load it axially, you cut a cross section, and guess what? Do you see any? You cut a cross section vertically. Do you see any shear stress on a cross section? No, right? You only see the axial loading, right? You only see the axial normal stress. Okay, yeah. But the question here is there any shear stress in the material at all, or not, right? So that's basically the question out here. Did you guys learn mode circle in the 260? Yeah? Okay. So that's basically the question out here. What do you think of the answer? Do you, for both of this, do you think there's still shear stress or not in the material? And the answer is yes. Okay. So there's still shear stress. So even though, for example, over here you don't see any shear force on the cross section, but it really depends on. But you know, actually emphasize here, how do we do the cut? The cutting of the cross section is what? Is vertical, right? So what if you don't cut it like that? What if you cut it like this, right? Or like this? Okay. It's not vertical anymore, right? Yeah. And then along that cross section, okay, and you will actually see the shear stress. Okay. And this is basically due to the next we're going to look at it. Okay, due to the transformation, okay, of this state of stress. Okay, and that's the idea of this is looking at this as a general state of stress. Okay, yeah. So instead of drawing that, I'll show you this stress elements here. I think actually I have that at the top here. So for example, right, this is the drawing of a general state of stress. And this is a 3D drawing, okay? This is a 3D drawing, so you have 6 sides of this cube, and then you draw all the possible type of stress on each side of the cube, okay? 3D. Okay. But in reality, right, so there is this basically 3D state of stress. Okay, 3D state of stress. But in reality, there is a very simple case. Instead of a 3D, basically all you have is actually just a 2D state of stress. Okay? And this is 3D state of stress. Sometimes we call it plane stress. Okay, plane stress. So the plane stress is easy to draw. So you have a essentially you don't really look at in a 3D. Okay, you only look at the planar description. Here's a planar description, and you draw all the possible stress on the 4 sides of here. So this is your sigma x, and this is your sigma y. Okay, and then here are your shear stress tau x y. Okay. That's planar. So let's start from the planar here. And all the time, in our case, what we deal with is actually end up with a 2D, basically state of stress or plane stress. So what transformation basically means is, so suppose this is the state of stress that you obtained when you do a vertical cut. Okay, you cut it vertically, and you obtain this state of stress. Okay. Now, as I said, you can cut differently, right? Yeah, different cross section, different orientation. So what that means is actually basically for the same state of stress, what you can do is you can rotate these elements about an axis, let's say pointing out of this paper. Right? You can rotate it like this. Okay. So if you rotate it like this, and for general rotation, let's say if you rotate it counterclockwise, okay, if this is original location and now it was rotated over here now, okay, so if you rotate by an angle of theta at here, okay, and then this is basically the difference, you may end up with, okay, a different type of state of stress. Okay, so that's the point of general state of stress due to rotation. Okay. So after rotation, and this is a different, basically, state of stress. Does that make sense? Right? Yeah. And this rotation, this one here, and you could think of, okay, this is probably a cut, right, in this direction. Okay. So one of the convention out here for the theta, okay, it's considered as a positive if it is a counterclockwise rotation. Okay. This is a convention here. So theta is a positive if it's considered as a counterclockwise rotation. So, and now here comes this two very special state of stress now. Okay, so you can think about the transition. You can keep rotating it. Okay, you can rotate it 45 degree, 70 degree, right? Now there are two very special locations. One is called principal normal stress. Principal normal stress. So what this basically means is you rotate and all of a sudden you find that the shear stress are gone, becomes zero. And at that location, okay, at this certain theta angle, all you're left with is the normal stress, and it is the maximum value for this sigma. So that's basically the state which is called the principal normal stress. Okay? Yeah. So at certain theta, okay, at a certain theta angle, sigma becomes maximum. Okay? And that value, the maximum value, is called the principal normal stress. That's very important to value because everything that we're doing is trying to find the maximum or the location that needs analysis. Then what is the maximum value? So the maximum value here, there are two directions. Actually, there's a maximum and a minimum. Okay, so sigma So the sigma 1 and 2, okay, representing this maximum value and the minimum value, okay, it can be obtained through this formula. Okay, so your sigma 1, 2 equal to this. The plus sign representing the maximum value, and the negative sign representing this minimum value here. Okay? Yeah. This is the principal normal stress. Okay, this is the principal normal stress. Similarly, if you rotate, keep rotating, and at another certain value, then you end up with this so-called, basically, principal shear stress. Okay, principal shear stress. And the principal shear stress is calculated as tau 1, 2 equal to positive and negative, okay, sigma x minus sigma y over 2 square plus tau xy square. So that's your principal shear stress for this in-plane case study here. Okay? Yeah. This is a very useful formula, and you actually will try to remember this one. Okay? Yeah. Closing so. Okay. Any questions so far? Okay. Okay, so now the next point here is, okay, well, how can we, this is two things here, right? How can we visualize this whole thing? Okay, how can we obtain a value other than this principal normal stress or principal shear stress, right? How can we interpret basically this rotational idea, right? This is essentially like a transformation idea here. So, and that's what the so-called Mohs circle, okay, will help immensely in terms of understanding of this transformation from one state to another state, right? To another state. Okay. So, the idea is I want to quickly show you how to draw a Mohs circle, okay, and how to interpret things based on the given mode circle at here, and especially how we can explain some of the phenomena based on the Mohs circle. Okay, yeah. So to draw a Mohs circle, there are a couple of conventions that we have to be clear. Okay, so the conventions mostly to deal with positive or negative conventions. Okay, yeah. So let's say if I have a state of stress. Okay, I have a state of stress element. This is a planar case. Okay, so this is your y-axis, your x-axis. Okay, number one. Okay, you need to be clear that what are the positive phase. So positive phase, there are two positive phase. Okay, so these two are the two positive phase at here. And then we'll have a sigma. Let's say we have a sigma x, sigma y, okay, and then tau xy for this planar case. Okay. So sigma x, sigma y, when they are positive, they are basically pointing outwards. Okay, pointing to the positive x and y-axis direction. Okay. So this is a two positive phase. Okay. So I'll just write down right here now. But now, when it comes to the for drawing in Mohs circle, okay, your sigma x, sigma y, okay, tension is positive. Okay, so if they're pointing outwards, the tension is a positive when it comes to draw Mohs circle. For the shear stress, this is the part a little bit awkward here. For the shear stress, it's the clockwise. Okay, the clockwise is positive. Okay, positive here. So if you look at the drawing and here, okay, this is considered positive because it's pointing outwards. Okay, this is basically for Mohs circle. But you look at the tau xy, the drawing in here. So this direction with tau xy will try to cause what? Try to cause this side of positive phase to rotate about which direction? But clockwise or counterclockwise? Counterclockwise, right? So when it comes to the Mohs circle drawing, and I'll show you, it'll be considered as a negative, right? Considered negative. Okay? Yeah. So this is your procedure. So I'll show you quickly how the procedures of drawing Mohs circle here. First step, and you draw a coordinate system with tau, sigma, and tau, okay, as x and y axis. Okay. And second step, based on the state of stress, okay, based on the state of stress, you figure out. Okay, so basically, I'll write it here. So number one, okay, draw sigma and tau, okay, axis. And number two, okay, mark the sigma x and the sigma y, okay, on x-axis. So let's say here's a sigma x, here's a sigma y. I don't know, maybe let's say this is 100, or maybe this is 80, or this is 40. Yeah, who knows, right? Yeah. So you plot the sigma x, sigma y along this axis. So suppose this is your, let's say, let's say this is your sigma x at here, and this is your sigma y at here, for example. Okay? Yeah. So that's your second step. And then third step, okay? So I'm going to call this as a positive face A, and this is a positive face B here, okay? For the positive face A and a positive face B, okay? So positive face A, okay? Positive face A, coordinates. Positive face A, write down the positive face A coordinates. And this is where you have to stick with the Mohs circle convention. So for example, right, in this particular case, if I'm going to write down the coordinates for this face A, it's sigma x, right? And then here you have a tau xy. So literally, you should actually write what? Negative tau xy. Because that tau xy will cause the direction will cause it to go counterclockwise. Okay, so then you find basically the location of the coordinates in the sigma and the tau x, the plane at here. So that basically will give you somewhere around here. So this is your negative tau xy. So this is going to be the location A at here, right? Location A. Okay, yeah. And third, and then the next step, okay, mark the origin O, okay, in the middle of the sigma x and the sigma y. So basically, here is your origin for the Mohs circle at here, okay, the origin of the Mohs circle. And finally, finish this circle, right, with OA as a radius. So here's the radius of the circle, and finish that circle with this radius at here. Okay, and that's the Mohs circle. Okay. Finished circle is OA as radius. Is that good? So that's very simple. Okay? Yeah. So before I finish it here, what can we get? What kind of information can we get out of the mole circle here? First of all, where is the principal normal stress location? Where is it? It's here and here. Okay? These are the principal normal stress. So this is basically your sigma 1 and sigma 2, right? Principal normal stress. And where will be the principal shear stress? It's at the top and the bottom here. So this is your tau max at here. Okay? Yeah. Right, that's clearly states what the value of the sigma 1, sigma 2, and the tau max. And second of all, right, here is your current location A, which is basically this is your state of stress that you started with, right? And here's your principal normal stress. So the question here is, how do I go from the current state of stress to the principal normal stress state? You need to go from where? From here to here, right? So basically means you need to rotate from the current location to here by this much angle, isn't it, right? But in mole circle, you actually, this is called 2 theta here, so you rotate half of that much. You rotate half of this much to get to the principal normal stress. And what direction is this rotation? In this case, it's a counterclockwise. Is that right? Yeah. So basically, if this is the current state of stress, then you rotate counterclockwise half of this much to give you the principal normal stress state of stress. Is that clear? Right? Yeah. So I'm going to make use of this knowledge next lecture to explain a couple of phenomena, right? Okay? Yeah. See you next the day after tomorrow.